There's a number quietly reshaping the entire tech landscape in 2026, one that's bigger than most national infrastructure budgets and rarely gets the spotlight it deserves. Nearly $700 billion. That's what the biggest players in the industry think. Microsoft, Amazon, Google, Meta, and a few others are committing this year alone to build the physical backbone of artificial intelligence. Not on flashy software or celebrity endorsements, but on the raw materials, the massive facilities, the specialized chips, the power systems, and the cooling tech that turn raw electricity into intelligent computation at a scale humanity has never seen before. This isn't hype or speculation from some analyst report. It's the actual capital expenditure guidance coming straight from their earnings calls and filings. A 60 to 70% jump from last year and more than triple what they were spending just a couple of years ago. And it's creating an infrastructure race that's accelerating faster than anyone predicted, with ripple effects touching everything from your electric bill to global energy policy to the future capabilities of the tools you use every day. Stick with me as we unpack exactly what's happening, why it's exploding now, who's winning and losing, the mind-blowing engineering feats underway, the real-world bottlenecks that could slow it all down, and what this means for the world that's being wired up right in front of us. To really appreciate the scale, let's start at the foundation, what AI infrastructure actually is. At its heart, it's the physical world that makes digital intelligence possible. We're talking about specialized processors, primarily GPUs from companies like NVIDIA, designed from the ground up for the massive parallel calculations that power large language models and generative systems. These aren't your standard laptop chips that handle tasks one after another. A single modern AI GPU can perform thousands of operations simultaneously, crunching through the matrix math that lets models predict the next word, generate an image, or reason through complex problems. A frontier model today might have hundreds of billions or even trillions of parameters, and training or running it requires clusters of tens or hundreds of thousands of these chips working in perfect synchronization for weeks or months at a time. Then you layer on the data centers themselves, enormous, purpose-built warehouses packed with server racks that are denser and hotter than anything from the pre-AI era. These facilities need ultra-fast networking to shuttle data between chips at terabytes per second, advanced memory systems to keep everything fed without bottlenecks, and sophisticated storage to handle the petabytes of training data involved. But the real game changer, and increasingly the limiting factor, is energy. A single high-density AI rack today can draw 60 to over 100 kilowatts, 10 times what a traditional server rack used to consume. Scale that up to a full cluster, and you're looking at megawatts of constant power draw, enough to light up entire neighborhoods or small towns. The latest projections show global data center electricity use surpassing 1,000 terawatt-hours this year, equivalent to the entire consumption of a major country like Japan, and that's almost entirely driven by AI workloads. In the United States alone, data centers could account for 6 to 12% of total electricity demand by the end of the decade, up from around 4% now. Inference, the process of actually answering your queries or generating outputs, now dominates, making up 80 to 90% of the demand because billions of users are interacting with these systems constantly, not just the occasional training run for a new model. This is why the spending has skyrocketed. The big hyperscalers realized a few years ago that the old model of renting generic cloud compute wasn't going to cut it for the next wave of AI. The scaling laws that researchers discovered show that more compute, more data, and bigger models don't just give linear improvements, they unlock entirely new capabilities in reasoning, creativity, and reliability. So ownership of massive, optimized capacity became existential. Amazon is guiding toward around $200 billion in capex this year, much of it for AWS AI infrastructure. Alphabet is in the 175 to 190 billion range for Google Cloud and its custom TPUs. Microsoft is pushing close to 190 billion, Meta 125 to 145 billion for its own accelerator chips and data centers, and Oracle adding another 50 billion or so chasing AI cloud deals. Add in players like CoreWeave and others, and the total crosses that 700 billion mark easily. To put it in perspective, that's more private capital than the entire global semiconductor industry invested in new fabs a few years ago, and it's flowing into a build-out that's compressing timelines from years to months in competitive markets. The pace is breathtaking when you look at real examples. Take xAI's Colossus supercluster in Memphis. They went from groundbreaking to a fully operational 100,000 GPU cluster in just 122 days back in 2024, then expanded it rapidly through 2025 into the hundreds of thousands, now pushing toward 500,000 GPUs or more across multiple phases, with some reports indicating it's already hitting gigawatt-scale power draws. They bypassed grid delays by deploying on-site gas turbines and battery storage right from the start, turning a former industrial site into one of the densest AI training facilities on the planet. Microsoft, meanwhile, struck a groundbreaking deal to restart the 3 Mile Island nuclear reactor. Yes, that one from the 1979 incident, securing 835 megawatts of always-on, carbon-free power dedicated to its data centers, expected to come online in the next couple of years. Google, Amazon, and Meta are all in on similar long-term power plays. Massive renewable purchase agreements, explorations of small modular reactors, hydroelectric restarts, and even co-locating new campuses directly next to power generation sites to skip the years-long wait for new transmission lines. None of this would be possible without rapid innovation in the hardware itself. NVIDIA's Hopper generation, with chips like the H100 and H200, became the workhorse for the initial boom, but the transition to Blackwell is delivering the next leap. A Blackwell-based GB200 system can offer 2 to 2.5 times the performance on key AI tasks compared to Hopper equivalents, with huge gains in energy efficiency per token generated. It supports ultra-low precision formats like FP4 that squeeze even more work out of every watt, and the architecture packs 72 GPUs plus CPUs into a single rack with next-generation NVLink interconnects running at double the bandwidth. That means fewer racks for the same workload, lower overall power draw per useful output, and the ability to tackle even larger models. Hyperscalers aren't betting everything on one vendor, though. Google continues refining its tensor processing units for specific workloads. Amazon is scaling Trainium and Inferentia for cheaper inference. Meta has its MTIA accelerators, and Microsoft is investing in Maya. These custom chips can be 20 to 30% more efficient for targeted tasks, which adds up fast when you're running at this scale. The infrastructure race extends far beyond the chips. Networking has to keep pace because in a cluster of 100,000 GPUs, every millisecond of delay in data movement compounds into massive slowdowns. That's driving demand for high-bandwidth optical interconnects and new Ethernet standards tailored for AI. Cooling is another frontier. Traditional air systems can't handle the heat density of these racks anymore, so direct liquid cooling, where fluid flows right over the chips, and even full immersion in non-conductive liquids are becoming standard, slashing cooling energy use by 30 to 40% in some deployments. Memory and storage have evolved too, with high-bandwidth memory modules and ultra-fast solid-state drives keeping data flowing without starving the processors. Construction firms, power equipment makers, and even utilities are scrambling to meet the demand, creating a supply chain boom that's lifting entire sectors. But it's not all smooth acceleration. Power has emerged as the single biggest constraint, overtaking chip availability in many cases. Grids in hotspots like Northern Virginia, Texas, and parts of Europe are already strained, with utilities reporting multi-year backlogs for new connections. The transformers and switchgear needed to step down high-voltage power are in global short supply, sometimes taking 18 to 24 months to procure. Water for cooling is another flashpoint. Some large campuses consume millions of gallons daily, raising concerns in drier regions and prompting a shift toward more efficient closed-loop systems. Construction labor, permitting delays, and copper cable shortages add friction, compressing what used to be 5-year timelines into 18-month sprints. Then there's the geopolitical layer. Most advanced chips still rely on manufacturing in Taiwan, creating supply risks amid tensions. Export restrictions limit the latest NVIDIA hardware to certain markets, spurring domestic efforts elsewhere, though those alternatives are still catching up. Countries like Saudi Arabia and the UAE are leveraging abundant energy to build their own AI hubs, turning the race into a contest for technological and economic supremacy with national security stakes. The economic ripple effects are enormous and mostly positive so far. This $700 billion is fueling jobs in construction, manufacturing, and engineering across the U.S. and beyond, while boosting revenues for chip makers, data center operators, and energy providers. NVIDIA's data center business has grown explosively on the back of this demand, with Blackwell and the upcoming Rubin architecture already sold out well into the future. Smaller AI developers and startups benefit too as compute costs per task drop, with each new generation of efficiency making advanced tools more accessible and spurring innovation in everything from drug discovery to climate modeling to personalized education platforms. On the consumer side, it translates to faster, more capable AI assistants, better search results, creative tools that were science fiction a few years ago, and potentially lower costs for services that rely on intelligence at scale. Of course, there are valid questions about sustainability and returns. Skeptics point to the environmental footprint. Data centers could double or triple their share of global electricity by the early 30s if trends hold, prompting a push for more renewables, nuclear restarts, and efficiency gains. Newer chips like Blackwell already deliver 25 times better energy efficiency for certain inference tasks compared to older generations, and hyperscalers are offsetting much of their usage with record renewable deals. Monetization is another watch point. Will the applications built on top of this infrastructure generate enough revenue to justify the spend? Early signs are encouraging, with AI driving meaningful growth in cloud revenues and new enterprise use cases emerging weekly. But the true payoff for agentic systems AI that can plan, execute, and adapt autonomously will depend on this build-out catching up to the software vision. Looking ahead, the race shows no signs of slowing. Cumulative spending could hit trillions by the end of the decade as clusters scale to millions of GPUs. Inference serves trillions of daily interactions, and new frontiers like multimodal models and real-time reasoning become mainstream. The winners won't just be the ones with the most raw compute today, but those who master power security, resilient global supply chains, and the integration of hardware with breakthrough software. Everyday life stands to change in profound ways. Accelerated scientific breakthroughs that solve long-standing problems in medicine and energy, more productive workplaces where AI handles routine cognitive work, and even smarter grids optimized by the very intelligence it's powering. At its core, this $700 billion infrastructure race is the story of humanity doubling down on the tools that extend our intelligence further than ever before. Every interaction you have with AI today rests on this invisible empire of silicon and power being constructed at breakneck speed. It might feel abstract or distant, but it's already influencing the energy you use, the economy you participate in, and the possibilities that will define the coming years. The build-out is relentless, the innovations are compounding, and the future of what's possible with intelligence is literally being powered up as we speak. The race is far from over, it's just entering its most transformative phase yet.